Hey everyone, and welcome. Today, we are diving deep into the language of motion. We're going to see how something as simple as a graph can unlock a whole toolkit for understanding and predicting how anything moves. This is some foundational stuff, especially if you're tackling Class 9 physics, so let's get into it.
So, have you ever wondered how we can predict exactly where something's going to be? You know, whether it's a car speeding up, a planet going around the sun, or just a ball you toss in the air? How do we know precisely where it'll be at any given moment? Well, that's the big question we're going to answer. Here's our game plan. First, we'll look at how to visualize motion. Then, we'll actually build the mathematical tools we need. We'll check out a cool special case, circles, and then see our tools in action. Finally, we'll touch on the biggest question of all. Why do things move in the first place? All right, let's dive right in. First things first, visualization. See, before we can predict anything, we have to be able to see the story that motion tells. And it all starts by turning a bunch of boring numbers into a clear picture. It all begins with just watching. Let's say we're tracking a car. Every 5 seconds, we write down its velocity. What we get is, well, it's just a table of numbers. It's useful data for sure, but it's not exactly easy to see what's going on, right? But here is where the magic happens. The second we take those numbers and plot them on a graph, bam! Suddenly, it's not a random collection of dots. They form a perfect straight line. Just like that, we've turned that dull table into a super clear visual story. And that straight line, it's screaming something really important at us. It's telling us that the car's velocity is increasing at a perfectly steady, constant rate. In physics, we've got a name for that: uniform acceleration. And trust me, this simple visual idea is the key to everything that comes next. Okay, so now that we have this visual blueprint, we can actually use it to forge our predictive tools. Let's see how this one simple graph lets us build the core equations of motion. This is where we create our toolkit. So think of this graph as our master blueprint. It works for literally any object that's accelerating uniformly. You've got your starting speed, which we call u. Then, after some time t, you reach your final speed, v. And the steepness of that line, that's your acceleration, a. Just by looking at the graph, we can see that acceleration is simply the change in velocity, that's the final v minus the initial u, divided by how long it took. It's really just the classic rise over run that you might remember, and it gives us our very first core definition. Now, if we just shuffle that definition around a little bit, we get our first really powerful tool. The final velocity is just the starting velocity plus how much you've accelerated over time. With this one equation, we can predict an object's speed at any point in the future. Pretty cool, right? But what about how far the object has gone? The distance. Well, this is where the graph is just brilliant. The distance it's traveled, which we call s, is literally hidden in plain sight. It's the total area underneath that straight line. So how do we find that area? Easy. We just split it into two simple shapes we already know, a rectangle on the bottom and a triangle on top. The rectangle's area is just u times t. The triangle's area is 1/2 times a times t squared. You just add those two together, and we've just forged our second amazing tool, the equation for distance. But hold on, there's actually another way to look at this. Instead of a rectangle and a triangle, we can see that whole shaded area as one single shape, a trapezium. It's just a different way of looking at it, and this little trick is going to give us one final super useful tool. So, by using the formula for the area of a trapezium and mixing in our first equation, we can do a little bit of algebra magic and get rid of the time variable completely. This gives us our third powerful tool. And what's so great about this one, it connects velocity, acceleration, and distance. It's perfect for when you don't actually know how long the trip took. All right, so we've got our toolkit for straight line motion completely nailed down. But, the world isn't all straight lines. What happens when things start moving in circles?
Let's just compare for a second. On the left, our acceleration was all about changing speed, getting faster or slower. But on the right, imagine you're walking along a path and you keep adding more and more corners. Eventually, that path becomes a perfect circle. You're not speeding up, but you are constantly turning.
And this leads to a really key and sometimes tricky idea. In what we call uniform circular motion, an object's speed can be totally constant, but its velocity is changing every single second. Why? Because velocity isn't just about how fast, it's also about which way. And on a circle, your direction is always changing.
So for this special case, we need a different kind of formula, and it's actually pretty intuitive. The speed, v, is just the total distance you travel in one lap, which is just the circumference of the circle, 2 pi r, divided by the time, t, it takes you to go all the way around. Simple and elegant.
Okay, theory time is over. We have built this awesome toolkit. Now let's put it to work. Because the real power of this stuff comes from actually using it to solve real-world problems. Let's get our hands dirty.
So here's our situation. We've got an airplane sitting at the start of a runway. It starts from rest and accelerates at a steady rate for a full 30 seconds. The big question is, how much runway does it need? We know U, A, and T. We need to find S.
So we just need to pick the right tool for the job. We look at what we know, U, A, and T, and what we need, S. The choice is obvious. It's our second tool, S equals UT plus 1/2 AT squared. We plug in the numbers. And since the plane started from a standstill, that initial velocity U is 0, which means that the whole first UT part of the equation just poof, it's gone. That leaves us with S equals 1/2 times 3.2 times 30 squared. A quick calculation and we get 1,440 meters. See? The toolkit works perfectly.
We've gotten really good at describing how things move. But if you stop and think about it, our entire toolkit is built around acceleration, the change in motion. And that leads to a much deeper question. Why does motion change at all? Well, this famous quote from Newton's first law gives us a huge clue. An object's motion doesn't change by itself. Something from the outside has to force it to change.
And that feels like the perfect place to wrap things up for today. We have built this incredible visual toolkit that lets us master the how of motion. But the why? Figuring out the nature of that external unbalanced force that gets everything going? Well, that's the next exciting chapter in the story of physics. Thanks so much for watching, and hey, if you found this helpful, be sure to subscribe to the A1 Institute YouTube channel for more. See you next time.